Hey everyone, welcome back to StepSolve, where we solve engineering problems one step at a time. Today we've got a classic static showdown, a fixed beam that's taking both a point load and a distributed load. We'll break it down piece by piece, find the reactions, shear forces, and bending moments, and finish with diagrams cleaner than a brand new drafting table. Grab your notebook, your coffee, and maybe your emotional support calculator, because this beam is about to bend, but we're not. All right, here's the setup. We've got a horizontal beam fixed at point O. At point A, there's a 500 lbf load pushing straight down. Then from B to C, we've got a uniformly distributed load of 40 lbf per inch spread over 6 inches. The distances are O to A equal 8 inches, A to B equals 6 inches, and B to C equal another 6 inches. So overall, this beam is 20 inches long, which means plenty of room for chaos. Our mission: find the reaction force and moment at O, then figure out the shear and bending moment all along the beam. Step 1. The free body diagram, because statics without an FBD is like coffee without caffeine. At O, we've got an upward reaction, RO, and a counterclockwise moment, MO. At A, slap that 500 lbf downward arrow. From B to C, the distributed load gets replaced with one single force, 40 multiplied 6 equal 240 lbf, acting downward at the midpoint, which is 3 inches from B. Now everything's simplified and ready for some good old-fashioned equilibrium. Time to balance the verticals. Let's sum forces in the y direction. Upward is positive because gravity already took the negative job. F equals 0, our 500, 240 equals 0. So R equals 740 lbf upward. That means our wall's holding up 740 pounds of, I don't think so. This wall's doing more work than I did during finals week. Next up, shear force. At the free end C, shear is 0 because there's nothing past the end to resist. At B, we've got that distributed section, so VB equal 40 multiplied 6 equal 240 lbf. At A, add the 500 lbf point load, but equal 240 plus 500 equals 740 lbf. And at O, the reaction of 740 lbf brings the shear right back to 0. Boom, equilibrium confirmed. If your diagram doesn't return to 0, congratulations, you've invented a new law of physics. Now for the fun part, the bending moment. Moments build up from the free end toward the wall, just like student stress before exams. At C, the moment is 0, easy win. At B, the distributed load creates a moment. 40 multiplied 6 multiplied 6 slash 2 equal 240 multiplied 3 equals 720 lbf in. Since it's sagging down, it's negative. MB equal minus 720 lbf in. Now at A, that uniform load acts over more length, plus the 500-pound point load jumps in to help. Crunch the numbers. Ma equal minus 2,160 lbf in. That's a big bend. This beam's feeling emotions right now. Finally, at the wall O, MO equal minus 40 multiplied 6 multiplied 6 slash 2 plus 14. 500 multiplied 8 equal minus 8,080 lbf in. So the wall must
fight back, nigga! Fight back, nigga! Fight back! Fight back!
That's a personal boundary. Time for the visual recap. Shear force diagram. Flat from O to A at 740 lbf. Drop to 240 from A to B, then linearly decrease to 0 at C. Bending moment diagram. Linear rise from O to A, then a smooth curve down to 0 at the free end. Everything checks out, and the beam survives another day in the world of statics. All right, engineers, quick recap. Reaction at O equals 740 lbf up. Moment at O equal 8,080 lbf in counterclockwise. Shear and moment diagrams, done. Beam equilibrium, flawless. If this helped you ace your next statics quiz, smash that like button, hit subscribe, and drop your next beam problem down below. Because at StepSolve, we don't just solve, we engineer solutions one step at a time. Catch you in the next one.